Hello friends, so far in this lecture you have seen about spring mass damper system, equation of motion, longitudinal mode, phugoid mode, lateral directional mode, different modes, spiral, roll, Dutch roll mode, and introduction to SAS, stability augmentation system. Today we will be focusing on transfer function. As you know, transfer function is given by the Laplace transform of output to Laplace transform of input, and assuming that all the initial conditions are 0, or you can say that the system was in equilibrium. We will be seeing what will be the response of a system if it's exposed to a different input signal. We will be dealing in this course with major two signals, that is impulse and a unit step signal. Now impulse signal. Mathematically it is defined as it is very large at t equals to 0. Second, it is very small for t greater than 0. And third, integral is 1. These are the basic property of an impulse signal. Now the shape of the signal doesn't matter. It can be either a rectangular shape or triangular shape, but it must satisfy this following conditions. Now practically a signal with a very large magnitude, it's practically impossible. So we assume that a signal for a short duration which is having an area of unit, or you can say integral in 1. So assuming this is a step signal, your duration will be zeta and its amplitude is 1 by zeta. So overall area is 1. Or in case of this signal, my amplitude will be 2 zeta and my duration will be 1 zeta. See, area is half into 2 zeta into 1 zeta, which will be 1. We have seen about impulse signal, so we will be seeing about unit step signal. Now where this impulse signal is, physically you can see this impulse signal during some collision, or when an object hits. For example, when you hit a nail with a hammer, the force is known as an impulse. Even for spring mass system, if you apply force for very short duration, the response of that system will be due to impulse. That response is called as impulse response. Now the second signal is unit step signal. As the name suggests, unit step means it will have magnitude equal to 1 for t greater than equal to 0, and magnitude is 0 for t less than 0. That means a signal exists for time which is greater than 0. That is, if I draw this signal, it will be a constant magnitude signal for t greater than 0, and it will be same magnitude at t equals to 0 also. Since unit is mentioned in this unit step signal, so my magnitude will be 1. If unit step, or in general if you call it a step signal, The general definition is it will have a constant magnitude for t greater than equal to 0. Now we will be seeing how the system responds when this input signal are given to its transfer function. So best will be taking a numerical, and that will explain how the system will respond when it is exposed to unit step signal. Okay. So let us consider the case of pure rolling motion. The differential equation given for pure rolling motion is pure rolling motion minus dl by d delta A into delta A plus dl upon dp into delta of p equals to Ix delta of phi double dot. Now further solving this differential equation, we will get minus of 1 by Lp into delta p dot plus delta p equals to minus L delta A delta of delta A divided by Lp. Now these equations has already been solved in previous lecture, so I am not solving step by step solution of this equation. We will get this final equation substituting the suitable values in the differential equations. Now where this Lp is defined as dl by dp upon Ix or Ix, sorry, L delta A is defined as dl by d delta A upon Ix, and we will be taking 1 by Lp minus 1 by Lp as tau. Now substituting this value in this differential equation, we will get finally delta p in time domain equals to minus delta A upon Lp 1 minus e to power minus t by tau into delta of delta A. So solving for the steady state of roll rate, we will get P steady state at t equals to infinity equals to minus L delta A upon Lp into delta of delta A. As you know, steady state is at t equals to infinity, what will be the value? It's known as steady state. Okay. Now since you know that we can write delta A, L delta A as CL delta A QSB by Ix, and L P as CLP B by 2 U naught QSB divided by Ix. Now substituting these two values in this equation, we will get PSS equals to minus CL delta A into QSB by IX, CLP B by 2 U naught QSB by IX into delta of delta A, or PSS B by 2 U naught equals to minus CL delta A by CL P into delta of delta A. For this differential equation, we have seen the steady state given by this particular equation. Now here we had to find a steady state for roll rate. Now suppose we measure the value of this roll rate from instrumentation for an aircraft, which can be easily measured using rate gyros. Suppose that if we measure these values, so using the measured values, if we know the geometric dimension of my aircraft, I can easily get the value of CL delta A and CL delta P. So this is a very good method of finding the derivatives of an aircraft using the measured value of steady state. This technique of deriving the aerodynamic derivatives using the measured value is known as system identification. Based on the previous derivation, let's see a numerical based on that steady state value derived. Suppose that for an aircraft, CLP is given by minus 0.285 radian inverse, CL delta A equals to 0.039 radian inverse, area is given as 18 meters square, value of B is given as 6.7 meters, inertia is given about x-axis as 4676 kg meters square. Step change of 5 degree, that is aileron deflection of 5 degree. So using this value, B by 2 U naught U naught is given as 87 meters per second. B by 2 naught equals to 6.7 by 2 into 87 equals to 0.039 second. Dynamic pressure Q equals to half rho U naught square equals to 4636 Newton meters per meter square. LP will be given as CLP V by 2 U naught QSB upon IX, which is equal to minus 1.32 second inverse. Tau, as we know, it was minus 1 by LP, so tau will be equal to 0.77 seconds. L delta A will be equal to CL delta A QSP upon IX it is equal to 4.66 second inverse. So steady state value of roll rate will be minus 4.66 into 5 degrees, since the equation for steady state value of roll rate was given by PSS equals to minus of delta A by LP into delta of delta A. So steady state value of roll rate at steady state will be minus of 4.66 into 5 divided by minus 1.32, which will give me 17.8 degree per second. So this is my roll rate, value of roll rate at steady state. As I already told you, if instead of calculating the steady state value of roll rate, if we measure the value of this roll rate from rate gyros, we will be easily able to derive the values of your aerodynamic coefficient CLP, CL delta A, since this geometric values is easy to determine for an aircraft. Let's take another problem for a second degree equation or second order derivative. Suppose for an aircraft the following data are given as Cn beta equals to 0.071 per radian, CnR equals to minus 0.125 per radian, Cn delta R equals to minus 0.072 per radian, Cn beta dot is taken to be 0 for velocity of 53.64 meters per second. Density at sea level is given by 1.2225 kg per meter cube. Area for aircraft is 17.09 meter square. Span 10.18 meters, and inertia, moment of inertia about z axis by 4786.04 kg meter square. Now you can do the calculation, as the formula for these derivatives have already been told and you can find it in any book. So I am just writing the values which will come upon substituting these values in that equations are: your dynamic pressure will be half rho V square equals to 1762.315 kg per meter second square, and beta will be 4.55 second square, and R equals to minus 0.76 per second, and delta R equals to minus 4.61 per second square. Now for pure rolling motion, the differential equation is given by psi double dot minus nr plus minus n beta dot into delta of psi dot plus n beta delta of psi dot delta of psi equals to n delta r into delta of delta r. Now, since we have already mentioned Cn beta dot is 0, so this term will be 0. So, rewriting this differential equation, we will get, and substituting the values for n beta, n r and n delta r, we will get differential equation as delta of psi double dot, this is delta, equals to minus 0.76 delta psi dot minus 4.55 delta psi minus 4.61 delta of delta r. Now, since psi dot, delta psi dot can be written as delta r, so we will get delta r dot equals to minus 0.76 delta of r minus 4.55 delta psi minus 4.61 delta of delta r. Now, as you can see, using these two differential equations, we can form a state matrix of the differential equation represented by psi delta of psi dot and delta of r dot equals to zero 1 minus of 4.55 minus 0.76 into delta psi to delta r plus 0 minus 4.61 to delta of delta r. So, this state matrix representation of differential equation is in the standard form of x dot equals to ax plus bu. Now, in such case, if you want to form the transfer function of this state matrix, we can use either Cramer rule, or simply you can use a formula as this will be s of I x taking Laplace transform of this state matrix equation Si minus A of x of s equals to bu. So, x of s will be Si minus A inverse into b u of, this is u of s, u of s. So, from this transfer function we will get x of s by u of s equals to Si minus A inverse into b. So, you can find transfer function using this formula or using Cramer rule. We will be seeing deriving the transfer function using both method. So, first using this formula, let us derive the transfer function S0 0 S minus my matrix A, which is 0 1 minus 4.55 minus 0.76 into x of s equals to B of u, which is 0 minus 4.61 into delta R of S. Okay. Further solving this, S minus 1, 4.55, S plus 0.76, X of S equals to 0 minus 4.61 delta of delta RS. Here my XS is nothing but matrix involving delta psi and delta R. Now, so my S will be S minus 1, 4.55, S plus 0.76 inverse into 0 minus 4.6.6, 4.61. Now calculating inverse of 2 by 2 matrix is very simple, which will be adjoint of this matrix. This was our A matrix divided by determinant of this matrix, which comes to S plus 0.76, 1 minus 4.55, and S and determinant is x square plus 0.76 S plus 4.55. This whole matrix multiplied by 0 and minus 4.1 will give me my value of XS. Now this multiplication is very simple, since first element is 0, so you will get X of S as minus 4.61 by your value of determinant, which is x square plus 0.76 S plus 4.55, and multiplying this row by this column will get minus of 4.61 upon S square plus 0.76 S plus 4.55 into delta R of S. So transfer function of this matrix will be, since we know that X of S is nothing but delta psi of S and delta R of S, this whole with respect to delta R of S will be delta R of S divided by delta R of S equals to value of this matrix 61 by S square plus 0.76 S plus 4.55 and minus, this is S, minus 4.61 S upon S square plus 0.76 S plus 4.55. So this is a transfer function for delta psi upon delta R. The transfer function is given by this equation, and for delta R upon delta of delta r, or radar reflection, is given by this particular equation. Set of transfer functions we have derived using your SI minus A inverse into B formula. Now let's see using Cramer's rule. Because why will be needing Cramer's rule? Because this is a 2 by 2 matrix, so finding inverse is very easy. But if you go for higher order differential equations, or a matrix which is large, say as 4 cross 4 or 5 cross 4, finding inverse is little bit tough. So in that case, Cramer's rule is very beneficial. We know that SI minus A x of S equals to B of U of S. This we got from substituting or finding characteristic equation. So now the value of SI minus A was S minus 1, 4.55, and S plus 0.76. Value of XS was delta psi S and delta R of S. Value of B was 0 and minus 4.61. U of S was delta R of S. So while deriving the transfer function using Cramer rule, delta psi of S by delta of delta R of S will be, just substitute the value of B matrix in the first column if you want to derive the transfer function for delta psi of S. So it will be determinant of 0 minus 4.61 minus 1 S plus 0.76 by determinant of S 4.55 minus 1 S plus 0.76. This is determinant of SI minus A. And similarly, for finding transfer function of delta R of S upon delta of delta S, you substitute the value of this column by the value of B matrix. So delta R of S by delta of delta R of S will be determinant of the matrix 4.55, 0 minus 4.6 divided by determinant of this matrix. Just solve this equation, you will eventually get the same transfer function as derived from using formula SI minus A inverse of B. Okay. Now the problem related to pure yawing motion. The transfer function for psi s upon delta rs will be minus 4.6 by s square plus 0.76 s plus 4.55, and transfer function for rs upon delta rs will be minus 4.6 s upon s square plus 0.76 s plus 4.55 s. Now when this transfer function step input signal will be applied, let me run this command and you can see the output for step input signal. So these are the responses of transfer function for a unit step signal. Now from the plot, as you can see, the steady state value for rs upon delta rs is 0. Let's see the characteristic of this transfer function's steady state and your settling time. Now the value of settling time for delta r upon delta r of s, final value for delta psi upon delta rs is minus 1.01. From final value theorem, as you can see, the value for transfer function delta psi upon delta rs will be minus 1.011, and for delta r upon delta rs will be 0. Now during our analysis, we saw a first order equation, a second order equation, and what will be the response of that when subjected to a step input. Now I want to discuss what will be the response of a higher order system when it is subjected to a step input. So in that case, the concept of dominant pole comes into role. So I'll be explaining what are dominant poles and how system responses to different input signals. So for that, let's take a system which is a second order system cascaded with a first order system. So my second order system, as you know, the standard second order system is represented by omega n square by s square plus 2 zeta omega n s by omega n square. This is my second order system. Now it's cascaded with a first order system, which is 1 upon tau s plus 1. So overall this will be a third order system. What will be the response when this is subjected to a unit step or impulse signal? We were talking about dominant poles. So let me explain what do you mean by a dominant pole. In this equation, as you know, your poles will be minus zeta omega n plus minus j omega n root over 1 minus zeta square. And for this case, as you know, it will be minus 1 by tau, s of minus 1 by tau. As you know, for in Laplace domain, for every root, the real part of the root, there is an exponential term corresponding to that in time domain, which results in decaying function or increasing function. That's why we go for real part to be negative, because for each real term there will be an exponential term in time domain. So if my real part is negative, my function will be a decaying function. If my real part is positive, my function will be an increasing function. This will result to instability. This is stable because at some finite amount of time this will finally reach a very small value, or you can say a zero value. So we were discussing about dominant poles. So in this case, in this scenario, you can have different cases. Now first case B, suppose this is a second order underdamped system and this is dominant pole. Now what do you mean by dominant pole? Now as I already told you, for each root in Laplace domain there is a corresponding exponential term in time domain, and if that is a root in a negative half of S plane, you will be getting a decaying function, as I explained in this e to power t. So for this case, as you know, response will be due to decaying response will be due to minus zeta of omega n, and for this particular case your decaying function or decaying response will be due to minus 1 by zeta term. So dominant means, suppose value of my zeta omega n comes to be minus 2, and the value of minus 1 by zeta comes, say, like minus 1, or let's take a larger value. Let's take that minus zeta omega n equals to minus of 5, and this equals to minus of 1. So corresponding to this term, we will be getting function something e to power of minus 5t plus second order, so sine term something will come, and corresponding to this value will be getting e to power minus t. Now since you can see the coefficient of this function is minus of 5t, so the function will decay rapidly. Suppose this function decays rapidly, say I take some random value, say about 3 seconds, this function reaches 0, and you can say the power of this particular function is 1 or minus 1, you can say. So this function will be decreasing but not as fast as compared to this function. So suppose it will be decaying, and after t equals to say about 20 seconds, this function reaches 0. So in this case my whole response depends on the root of first order function. Since for collective system your whole response should reach 0, so because of the value of this particular root, my whole transient response will be 0 only when this particular response due to minus 1 is 0. So I can say that my response of this particular system depends solely on the response of first order system. So I will call this as a dominant pole. Let's see what will be different cases and what will be response of that system. Let's discuss case 1. This is my second order system, is an underdamped system with damped system with second order poles as dominant pole. Second order system, dominant pole. Now in this scenario, when this scenario is there, percentage overshoot will be less as compared to a purely second order system. Your settling time will be less as compared to second order system, but your rise time will be more when compared to a pure second order system. Now second case, case 2, when both first order pole and second order pole are dominant poles, that is, this is my Laplace domain. My first order pole correspond to some value, say minus 1 by zeta, 1 by tau, and your second order poles will be, as you know, there will be two conjugate poles, so it lies somewhat about here, so that is all coincide in the same particular line. Then in this case both first order and second order are dominant poles. The result in this case will be, you will get a critically damped system which will be very similar to a second order system. The response will be similar to a second order critically damped system. Case 3, when first order pole is dominant pole. When this is a scenario, your response will be similar to second order overdamped system.
We saw higher order system, that is a cascaded system in which a second order system was cascaded with a first order system. So we'll be seeing the response of that cascaded system to a step input signal. Let me take a first order transfer function as 3 upon s plus 3, and a second order transfer function as 9 upon s square plus s plus 9. Now the case 1 which we discussed was the second order poles will be the dominant pole. The response of this cascaded transfer function with respect to second order system is the response of this cascaded system to step input signal will be for case 1 for case 1, as you can see, these are the responses of transfer function with respect to step input signal. The first order is represented by blue curve. Your pure second order system is represented by red, and your cascaded system is represented by this orange curve. Now, as per the properties of the cascaded system, since the roots of the second order system are the dominant poles, so the characteristic of this will be, as discussed in the class, the settling time will be less than the settling time of your pure second order system. So your settling time for second order system is 7.64 seconds, while for cascaded system it's 6.93. As you can see, the settling time for cascaded system is less than the settling time of pure second order system, and your percentage overshoot for the cascaded system will be less as compared to your second order system. Now this is the value of percentage overshoot for pure second order system. You can see peak amplitude is 1.58, and for cascaded system the value of peak amplitude is 1.38. So percentage overshoot has decreased from 58.3 to 38.3 percentage. Similarly, we told that for a cascaded system, your rise time will be greater than the rise time of pure second order system. The rise time for pure second order system is 0.395 seconds, whereas for cascaded system it's 0.532. Now, as for case 2, where both first order transfer function and your second order transfer function have dominant root, in that case the transfer function I have taken as s upon s plus 3, while the second order transfer function is s square plus 6s plus 9. The roots will be minus 3 for first order system, and for second order system it will be minus 2 plus some complex part. So in that case the response to the step input signal will be as described with these plots. This is a step input which will be same since I have not changed the transfer function from case 1. Now this is a pure second order system represented by red plot, and your cascaded system represented by orange plot. As I told you in the class, the response for this curve will be close to or very similar to a critically damped system for a pure second order system. As for the third case, the transfer function which I have taken for first order system is same s upon s plus 3, while for second order system it's 9 upon s squared plus 7s plus 9. So that makes my zeta greater than 1. So in this case my dominant pole will be due to first order transfer function. In that case my response to step input will be as follow, by represented by this plot. In this case the response of the cascaded system is similar to the response of an overdamped system due to pure second order system.
So far we have discussed about second order system, first order system, your cascaded system, what will be the response of that when exposed to step input or impulse signal. Now, as you have studied in previous lectures, this is a longitudinal small perturbed equation of motion. So what will be the transfer function of that? So that will be derived using, this is a differential equation. Take Laplace transform and you arrange in matrix format, and as you know, to derive transfer function the best method will be using Cramer's rule. Use Cramer's rule to derive the transfer function for u of s upon delta E of s, alpha of s upon delta E s, and theta of s upon delta E of s. You will be getting a transfer function of the format something numerator in terms of s divided by a denominator, and as we saw in previous lecture, the denominator was same but the numerator quantity differed from equation to equation. So here also when transfer function will be derived, the denominator is same while numerator will have different coefficients. So this is a pretty long equation, and I would like you to do it yourself because there might be some error while equating this lengthy equation, but I have still tried to solve this equation, this matrix, and the coefficient, this d of s or your denominator I got was of the fourth order, and the coefficient for a, b, c are respectively given as mentioned on the blackboard. This is a1 or a, your b, c, d and e. This is very big equation. I would like to say that try to equate, no need to memorize this big equation, try to equate and see, because substituting this value, substituting the value for a general aircraft, this will be much simpler matrix to solve. Similarly, for the numerator part, for u of s upon delta E of s, you will get a third order equation. Similarly, for alpha of s, you will get a third order equation. Theta of s, you will get a second order equation. I'll be posting this on the forum, what will be the coefficients of AU, A alpha, A theta. So no need to worry about that, or no need to memorize this equation. So taking this equation of motion for longitudinal motion for a general aircraft, the following data, if I take the value of A equals to 675.9, B as 1371, C equals to 5459, D equals to 86.03, and E equals to 44.78. The value of A to E, if you take for a general aircraft, the transfer function for each of this will come to be u of s upon delta E of s will be minus 6.312 s square plus 4927 s plus 4302 by 675.9 s to power 4 plus 1371 to the power of 3 plus 5459 s square plus 86.31 s plus 44.78. Your alpha of s upon delta E of s will be minus 0.746 s cube minus 208.3 s square minus 2.665 s minus 1.39 divided by 675.94 plus 1371 s cube plus 5459 s square plus 86.31 s plus 44.78. And similarly, my value of theta s upon delta E of s will be minus 208.1 s square minus 136.9 s minus 2.380 divided by the same denominator. I won't be writing that. Okay. As you have seen in previous section, we derived transfer function for longitudinal perturbed equation of motion. Similarly, we can derive transfer function for lateral direction equation of motion. The set of equation or differential equation is given by these formulas. Now again you have to apply Laplace transform and write it in matrix form, and as you know, using Cramer rule you can derive transfer function for different variables of lateral directional equation of motion. Now I haven't derived the full equation. What I will do, I will put that the full transfer function on the forum and you can check. Now based on this transfer function and using a data for a aircraft, my transfer function for different variables will be given by this transfer functions, these equations, where since you know that lateral directions are controlled by two deflection surfaces, that is aileron and rudder. So transfer functions related to ailerons are given by this particular set of equations, while for rudder it's given by this particular set of equations. I would like you to practice more problems on transfer functions. Thank you.